Okay, welcome back, everybody. I had a little bit of a delay here, a little technical problem, but I'm back online. Okay, what is this, the fourth week? I believe so. Everything was graded, exam-wise has been graded, so take a look at your exam. I will open it up. I got to check with the other sections and when we can open it up so you can see your answers and the correct answers. When that occurs, I will send an email and say, hey, the exam will be opened up at a certain time. And then you can go in there and take a look. Right now, I don't believe it shows your answers. That's the way they set that up. Okay. And it's good so you can use it for at the end when you're getting ready for the final, because the questions are, very similar. Okay. Anyway, the average is somewhere in the 70s. That's about average for all the other sections. So first one sometimes could be a little bit challenging, but I think the others are kind of all in. We had a lot of information to give you in the first three chapters. Okay, so any questions, comments, concerns about where we're at this point and where we're going? Because I'm going to start on the next chapter, which is chapter 5, which is pretty good. We're ahead quite a bit. So, any questions? All right. Well, let us continue with chapter 5. Now, if you recall, when we were talking about the atoms, the subatomic particles, the proton, a neutron, and the electron, we gave them or assigned them, they were assigned atomic mass units or relative mass units because these guys are so tiny. So protons and neutrons are given an AMU of 1, a whole number 1. And the electrons, because they're so tiny, was essentially given a 0 with respect to an atomic mass unit, treated as weightless. And that's true. As powerful as these electrons are, they are tiny. And being so tiny, much more than the protons and the neutrons, that they behave like light. Okay, so our model up to now, I've kind of rehashed a little bit, is based on J.J. Thomson and Rutherford and so forth, is that we have the nucleus, which consists of the protons and the neutrons in the center, have a lot of mass, and then the electrons are somewhere orbiting the structure, and there's a lot of empty space between the two. These electrons are not just sitting there, but it's been shown that based on our model that they are in orbits and they're moving around. Okay. Now, how do we know this? We're going to learn that these atoms, these elements, under certain conditions, can lead to a better understanding why these electrons are in these energy levels. But a quick note about energy levels, and we briefly talked about it in the last chapter about energy, in that atoms and matter, with respect to atoms in general, but here we're going to be talking mostly about electrons here eventually, is that they are in what is called a ground state, a stable state. Mother Nature being nature is, it's not going to be hopping around to the next stage unless you put energy into the system. And there's evidence of that all around us. The screen that we're looking at right now is evidence for being from an excited state to ground state. Because the image that you see is the result of the atoms on your screen that have gone from the excited state down to the ground state. They're up in a high excited state and go back down to the ground state. And in that process, because of conservation of energy and matter, they have, what occurs is whatever amount of energy you absorb to go to the excited state, you're going to release that energy, okay? And you release that energy either as heat or light. And so on the screen, what we're viewing is these atoms on our screen, our monitor, that are going back to the ground state. Fluorescent bulbs, or any bulb, is another example. It just happened so fast to us, and our time, it looks like it's continuous, but if we were able to stop time, slow it down, and look at a fluorescent light bulb, it will flicker. And it will flicker like a strobe light, because what's happening to the gas, the molecules in that bulb are being excited by the electricity that's placed into the gas in the bulb, and they're excited to be push up to the excited state, and then when it comes back down, they emit that light, they emit that energy, they absorb as light, and hence we have light. Be it an LED, be it an incandescent light, it's a matter about energy. Okay, so with that in mind, we need to talk a little bit about light, okay? Because we're going to apply what we learned about light into the electron to extrapolate. So we know that light, exists as wave, okay? And electrons, as I stated, can also exhibit wave properties because they are so tiny. So how do we demonstrate what a light is? Well, we have this graph here. It's a wave of light propagating through space, okay, having hills and valleys. So here they call them crests and throws, but hills and valleys. Now what we can do is if we mark a spot, let me change my color here. If we mark a spot anywhere, let's say on top of the hill, and then if we go over to the next hill, that is what we call a wavelength, okay? And we denote that with that symbol lambda, okay? Has a very specific wavelength. It's an entity that can be measured. Light around us has different wavelengths. Our eyes can only observe a very small, we have a spectrum actually, that in this spectrum, on one end of the spectrum, we have radio waves. We're all familiar with radio waves, okay? Listen to your radio on your car, very specific wavelengths. And then in the other end of the spectrum, of this electromagnetic spectrum, we have gamma rays and X-rays, very specific. We all know that X-rays have high energy, can be devastating, and gamma rays have a lot of energy and can be devastating. Whereas radio waves, not so much, as far as we know, as far as having a problem with any type of energy associated with it. It has some energy, but not as strong as, say, gamma. So anyway, all electromagnetic radiation, which includes electrons, have a specific wavelength, okay? And that is denoted by that symbol called lambda. Now, the frequency is how many wavelengths occur in a given unit time, which is normally a second. Treat it as a beat. So you hear a beat, and in the 1 second, how many beats do you hear within that 1 second? That is called the frequency. So we got lambda, which is the distance between peaks. Now I just picked the peaks, but you can pick any area. You could have picked the valleys here from here to here. That is the same distance that was denoted up here. Okay, you can pick any point. You can pick the hill of one wave to the hill of the other, and that is the same wavelength. Whichever area you pick, you can be the same area on the next wave. So we call that lambda, or wavelength. That's the distance between peaks on adjacent waves. Within a given time span, you have what we call frequency, and it looks like a V symbol. It's a Greek symbol, but we call that frequency. And you're familiar with these too, okay? You may have heard the name Hertz, and I don't mean to rent a car place, but Hertz is the units for frequency, and that's how many wavelengths occur within a given time, which is normally 1 second. Your cell phone, your electronic device, anything that has a a brain, a processor, is operating at a certain speed. Your computer could be operating at, say, 2 gigahertz. You go through your about of your computer and check it out, and it'll tell you how fast your processor is. 2 gigabytes means that in 1 second, there are 2 billion things occurring, iterations occurring in your computer. Obviously, the bigger. Now, I come from the old school, way back when I first began, where that computer speed was in megabytes, megahertz, okay? 1,000 is very slow, okay? 3 mega. Now we're in the giga. For most computers, I hear 3. Obviously, if you're into gaming, you want a high processor, the process. But, as a side note, look at your bus. If you have a very high speed processor, but your bus is operating at a low rate, defeats a high processor. It'd be like me, an old man like me driving a Lamborghini. I got a nice fast car, but I want to keep it at the speed limit, right? Okay. Anyway, so hertz is frequency, and that's how many cycles occur within a given time, which is normally 1 second. All right. So this depicts a long wavelength on top of X amount of value. We're just doing a relative comparison here. You can see that when we look at, let's say here, the frequency of the bottom one, we have this arrow and that arrow. That is the wavelength, or lambda, for the bottom wavelength compared to the distance of wavelength of the one on top. Okay, so you can see graphically that the graph, or the depiction on top, is a depiction of a wavelength that is longer than the one in the bottom. Okay, so 2 things to take away from this. Long wavelengths have what we call low energy light. Okay, so there'll be an example of, let's say, radio waves. They have low energy. Okay, they also have a low frequency. Well, what do we mean? Let's say this distance from the 2 lines from here to here. Let's say that was 1 second. Okay, the time distance was 1 second depicted there. Well, if you look at the top wavelength, you see that 1 wavelength occurred, from one hill to the other. So we have basically 1 hertz. Okay. Whereas at the bottom, we got 1, 2, 3, maybe about 3 hertz within that time span between the red arrow here. Okay. 1 second. Top one only had 1 wavelength pass through. Bottom one has 3 wavelengths, so 3 hertz. So the bottom one has, relatively speaking, a high frequency relative to the one on top, which has a low frequency. Okay. The short wavelength has high energy, and that could be associated with X-rays. We're all familiar with X-rays. They're strong. Okay. You go to the doctor, get an X-ray, they go right through your body. You get an image. Gamma rays can even cause more damage. And so you have high energy for short wavelengths, but they also have a low frequency for a given time, but the wavelength is small. Okay, small wavelengths, high energy, high frequency. Long wavelengths, low energy, low frequency. Okay. All right. In this scenario here, you're asking you to compare the two, and you're asking, well, which wave has a higher energy? Well, you can see here just by looking at it, the wavelength B has a higher energy, short wavelength, okay? Very short wavelength. So lambda B is very short compared to lambda A. Here you go. Give me 2 seconds. Okay, I'm back. All right, so depicted here, the top graph shows is an example of compare the two, has a higher energy, and A would have the lower frequency. Okay, now here's the spectrum I just talked about. On the far right represents radio waves, very low energy, very humongous wavelengths in the meter range. And then to the far left, you can see depicted there are the gamma rays, which is very short wavelengths and very high energy, very high energy. We as can only see a very small, now this spectrum here is not the scale. I wish it was, but you'll see that overall, the wavelengths that we actually see is very small. That is, obviously we call that the visible, okay? The visible. And to the right, if we have larger wavelengths, we have the infrared, and then obviously right before the radio waves, we have the microwave. That's where you go do your popcorn thing, okay? All right, so yes, your microwave is actually shooting electromagnetic radiation to your popcorn, okay? The water in the popcorn absorbs that energy from the microwave because there's associated with all this electromagnetic radiation and X amount of energy. And so the water absorbs that energy from the microwave. The water molecule gets excited and goes up to the excited state and then drops back down. And in the process gives off that energy it excited as heat, and that heat is dissipated around to the popcorn. And, after 3 minutes or so, poof, you got a bag of popcorn or an amount of heated material, whatever. And then on far right are gamma rays. Gamma rays extremely deadly, very, very high energy. Here, obviously, we got the X-ray. Ultraviolet, a lot higher energy than visible. Spend a few hours out in the sun, you get a little sunburn, you get too red, it hurts a little bit. UV, too much UV can cause problems for multiple things, skin cancers, affect plants and so forth, a lot of problems. Then obviously we're over here. Now everything else in between we can't see because our eyes have cells in our eyes called cones and rods that they're only specific for certain wavelengths, so we can only see shades of gray or color depending on how bright the light is. But we do have instrumentation that allows us to see infrared, allows us to see UV and so forth, and X-ray. All right, so that is the spectrum. Be familiar with the spectrum, okay? Now, previously recall that we were talking about 1900s, we were talking about J.J. Thomson and all these scientists. Well, I said that there are other scientists, okay, in this time period. Sure enough, 1900, there's a guy, a scientist, German scientist called Max Planck. He's the Max Planck Institute in Europe is named after him. Okay, Max Planck in 1900s proposed a controversial idea for this time period. He proposed that energy was not continuous, but was emitted in packets or bundles, which he gave the name quanta. So there's packets of energy, okay? So it's not a continuously emitted quantity. And he named these individual units of light energy, and it should be like electromagnetic radiation, as a photon. And so here comes Star Trek and creates a photon torpedo. Okay, a little side note. Okay, so he coined the word quantized, that energy exists in levels and is not continuous. Okay, he proposed it, and a good example would be this wedge on the left where the ball is rolling down, and it's all that represents continuous energy. Okay. His proposal was, no, it's more like stair-step. And you can see here is in this cartoon where the individual is going up a level. That level is an X amount of energy. So there's an X amount of specific energy going from the bottom ground to the top level. in each step, okay? All right, so that's Max Planck. Proposed the idea of quantized energy, specific energy levels, okay? Niels Bohr. Now he Niels Bohr, another scientist, look at this, 1913, so we're still dealing here. Another scientist involved here obviously is Einstein, but Einstein was not alone. A variety of other scientists involved here. And we're only touching on a handful of these guys. So it's really mind boggles me that this time period, 1900s, we just have a whole plethora of stuff that just occurred. It's just, we had a lot of stuff that was being discovered and proposed. Niels Bohr proposed, talking about taking the idea of what Planck brought in. He said that electrons orbit the nucleus, okay? And they occupy orbitals with specific energy levels, analogous to the sun, and then we, as the planets around us, are at a specific distance away from the sun. That distance represents a specific amount of energy. So electrons, he proposed, are quantized. This is Niels Bohr's model. Now, up to this point, we had no idea, no model as far as how the electrons are around the atom. And that's where Niels Bohr brought into case. So he said the electrons orbit the nucleus, kind of like a planet around the sun, but more in three-dimensional, okay, rather than, two-dimensional where you got the Earth just going around the sun. It's not just going in different areas. So we got the electrons orbiting the nucleus in some space away, X amount distance away from the nucleus. And these distances are called energy levels or shells. I'll stick with the word energy levels. And there's 7 of them, okay? So what I'm going to do here, if you have your periodic table, I would take it and label them, okay? Starting with hydrogen, so that represents the energy level of hydrogen all the way across to helium. Starting at energy level 2, lithium all the way across to neon. Sodium for energy level 3 goes all the way across to argon, okay? And so forth. And this stops here at calcium. And we're going to have, and then it kicks up again at gallium, which is right here, okay, with energy level 4. These guys in the center, they also have an energy level, but they're going to have a different number for them, okay? So we got 7 energy levels, all depicted on the periodic table, as I drew them, with the numbers 1 through 7. We're going to use that to help us do what we eventually called the electron configuration, because the electrons we're going to learn, based on the model, that they occupy in what are called suborbitals. Not only are they in a specific energy level, within the energy level, there are other suborbitals, okay? Now, each orbit has a specific radius and therefore a specific energy level, from radius being from the distance of the nucleus, okay? So one way to depict that is if we draw this picture here, and these dotted circles represent the energy levels. Keep in mind, we're talking three-dimensional. We're just showing a two-dimensional model here, picture, so we can see that. Now, in this one here, this picture here, is only showing 7 energy levels. So, 3 energy levels, but there are 7, okay, depicted by the dotted circles. Now, how do we know this? Okay, well, we have what are called line spectra. Okay, and this is why we scientists came up with the model. Now, what exactly is a line spectrum? Okay, because what was done, much like light bulbs, we have neon lights and so forth. They took gas and sealed it in what's called a discharge tube, which is basically a fluorescent bulb, okay? Fluorescent bulb. And then stimulated or excited the molecules in that sealed tube. And guess what? They emitted light. Okay. And in the process of emitting this light, that light was analyzed. That light was processed through a prism, and we have a diagram of that. And guess what? It actually, and then that light was then run through a prism, which spreads light into the different wavelengths. The result was that what we call an emission line spectrum was observed for that particular element compound that was being excited with electricity. Okay? This kind of breaks it down a little bit, kind of gives you a generic diagram. You have, in this case, hydrogen gas, which is put in a tube, glass tube, like a fluorescent bulb. And then electricity is run through it. Electricity energizes the hydrogen gas, emits light. It runs through these slits, basically just to focus the light that's being emitted, okay, from the bulb. And then it runs through a prism. Prism, like I stated, what it does is separates that light into their different wavelengths, just like a rainbow. If you look at the rainbow after rain, they get the light, the visible light gets broken up simply because of the water droplets of the rain that break it up, and hence we're able to see the rainbow. So the prism breaks it up, and then we're able to observe what happens. And this is the emission line spectrum for hydrogen. This emission line spectrum is very specific. It is the fingerprint for hydrogen, okay? And that's how we can identify what's out there in other places of our universe, because we analyze the light. So light coming at us is very complicated, so there's some complicated instrumentation that allows us to analyze it. And from the analysis of the line spectrum, we're able to determine what elements we observe. So hydrogen all by itself emits these lines. And you can go through the calculations, which is beyond the scope of this class, and assign wavelengths. And these represent the energy levels that the electrons were at to begin with, okay? And they got excited to the next energy level. And when they come back down, they emitted energy, okay? Those numbers in the bottom of here called N, letter NM, those are nanometers. Nanometers, about 10 to the negative 9 meters. Those are the wavelengths that were analyzed. Okay. All right, so then clear my drawing. If we do this same thing with a variety of different elements, they each have a different emission spectrum. So each of it is a unique color in the unique wavelength. And like I stated, it is the fingerprint for that particular element. So you got lithium there, sodium, potassium, etc. Okay. Now, what is happening here? To explain what I just did verbally, basically explain as a diagram. We have here an example of the red represents an electron that's orbiting around some element. Okay. Now, we take that element and we apply energy to it, either in the form of heat or electricity. That molecule, that element, whatever, will absorb energy of a specific wavelength. Okay? And the electron, who was in the ground state, which is the first energy level, gets excited to the next energy level. Notice it's a specific energy level. It just doesn't throw it out there. Well, it's not a stable state at this point when it's in the excited state. And so it's going to hang out there for a bit, and then it's going to go back to the ground state. And in the process of doing that, it then emits that energy, conservation of energy, back to the environment, and it emits it either as heat or light. If you have an electric stove at home and you turn that on, do not the coils get red? Same thing's happening here. You turn the electricity on, that metal atoms get excited, they're gaining that energy, they have to emit it, and when they emit the energy, they emit it as light, some red light, and guess what? A lot of heat, and that's why you're able to cook those electric stoves, okay? All right. So each element has its own energy levels that are unique. So at this point, we have 7 energy levels that have been based on our model. Now, can this model change tomorrow? By all means, nothing is etched in stone. Believe me, new stuff is coming out all the time. And right now, this is the model that best fits the experimental data. Now, is it a correct model? Well, based on what we know, what we have, yeah, well, based on what we know. Is it correct? Your guess is good as mine. Nothing's 100%. Don't ever let a scientist tell you that everything's 100%, because it's not. He or she should be the first person to tell you, there's always probability of something else happening. Okay, so we got 7 energy levels. Now, within these 7 energy levels, and let me tell you, all these orbits, all these sub-levels that we come up, all this model is all mathematics. It's called quantum mechanics. You may have heard that term someplace. It's all some high-level mathematics. And what's even more fascinating, all of it's basically based on the hydrogen atom. And hydrogen atom, very simple model. But then when we get into, higher elements, it gets very complicated. So there's a lot of assumptions that occur, okay? And unfortunately, we have to make them because these equations, mathematical equations, get pretty crazy looking. So there's some assumptions made. And that's why I say, at least right now, this is the best model we got. So we got 7 energy levels. We have what are called sub-energy levels. And what these represent are these mathematical equations that I just explained that represent a 3-dimensional model of where the electrons exist within the energy level. So we have one group called S, all right? And then we got P as in Paul, and then D as in David, and F as in Fred, okay? I want you to keep this in mind. There are 2 S suborbitals only. There are 3 P orbits, okay? There are 5 D delta sub-levels or suborbits, and there are 7 different types. These are mathematical equations that when you take those mathematical equations and you plot data to them, they give you a picture, okay? And this picture represents the probability of an electron in that given space, okay? All right, so, but S, there are, excuse me. Erase that 2 on the S and put down 1. Sorry about that. Okay. Only one type of S orbit, 3 different types of P, 5 different types of D, and 7 different types of F, all of them with distinct shapes, okay? Distinct shapes. Now, a bit of more information. Every sublevel, the maximum electrons, max electrons, I have some more pictures here in a bit, electron per orbit, so orbital, or sublevel, maximum, okay? The maximum you can put in each sublevel is 2 electrons. So if you take the S orbit and there's 1 only, the max electrons that can go in an S orbit is 2, right? 1 orbit, 2 electrons total. The P I stated, there are 3 different types of P orbits. Each one can handle 2 electrons. So guess what? It can, all the P orbits, there's 3 of them, can handle a maximum number of 6 electrons. The D, there are 5. Again, like I just stated, each one can handle 2 max. So what do we got? We got 10 electrons for the D that we can put in. Anybody that has a D orbital, the maximum number of electrons I can put in there, those D orbitals are 10, which means if I got 11, I got to put it someplace else. Okay? See that? See how that goes? We start again with the S. The maximum I got is 2. So if electron number 3 comes into play, I can put it in the S mark because it's full. So I got to go to the next orbit, which more likely is a P. Okay. And then the F, of which there are 7, each one can handle 2. I can put in 14 electrons in all the F orbits of a given energy level. Because not all the energy levels have an F. Not all the energy levels have a D. And not all the energy levels have a P. But the first energy level definitely has an S. All right. And I'm going to use the periodic table to show you, demonstrate there. I'm going to first tell you about an equation you can help you out, or I can just help you and show you how you just use the periodic table and works like a charm. All right. Without having to sit there and memorize that crazy equation. Okay. So let me clear my table for a second. All right, so here we go again. I just stated the first energy level, the very first energy level, which if you look at the periodic table, and I show you that number 1 only encompasses hydrogen and helium. Okay, that's all they have, the S orbit. That's it, just one S for the first energy level. And we depict it with the numerical 1 in front. It tells us the energy level you're at. So guess what? That 1 could be from 1 to 7. All seven energy levels have an S orbit, all of them. So there's 1s, 2s, 3s, 4s, etc. to 7s. Okay. The second energy level also has an S, but this is where the P starts. Okay, so the second energy level has an S and a P energy level. They have 1s and 3p, 2p energy levels. Again, the coefficient in front represents the energy level it's in, and the letter represents the suborbital. As we go to the next energy level, which is the third period, okay, we introduce the D. That's what I said. If you pick an element, there's an element in the second energy level, they do not have a D. Not until you get into the third energy level. But their coefficient again represents the energy level. We still have an S, the P's continue, and then we introduce the D. So from this point forward, 3D, 4D, 5D, etc. Okay. At the fourth energy level, which is probably where we're going to stop, we introduce the F orbits, sublevels. Okay. And yes, we have the 4s, the P's continue, the D's continue, but then we introduce the F. Okay. All right, and it's probably the highest level. Now we're in some pretty big elements, and we probably won't go in detail further down in the F, but definitely just to refresh your memory, we will have a 5s and a 6s and a 7s. We will have a 5p, okay, 6p, okay, 7p. We will have a 5 David, 6 David, and down the road we could even have a 7D. Same is true with the S, okay? Now, obviously, there's only 118 elements now. We are working, there is research out there right now. They're trying to make 119, anything over. So energy, what's going to happen? We're going to end up with 8 energy levels, okay? And so, but we're not at that point yet. 6F to 7F, okay? So eventually we'll get into the 8 as we make more elements. All right, so I was going to state something, but no. All right, so this here, again, is a two-dimensional diagram of the energy levels I just talked about. First energy level, second, third, and fourth, okay? We got the S, the 2P, the S and the P, the SPD, and the SPDF for the fourth energy level. Okay, so orbitals, or the sub-energy levels, are regions of space where there's a high probability of finding an electron. These are these mathematical equations that were deprived from the models in quantum mechanics. And these equations then, when you plot data, gave you a picture of that equation, okay? And so this, again, here tells you, just to rehash, that the S, there's only one S orbital. And it can handle, each orbit, remember, can handle 2 electrons. So there's a maximum 2 electrons for the S orbit. The P's, there's 3 P's, each one can handle 2, so there's 6 electrons max. The D's, there are 5 orbits, 10 electrons, and the F is 7, giving us 14, okay? So each sublevel contains a specific number of orbitals. Now this box here, it really should be upside down, because when you fill these electrons, obviously you don't start filling electrons with the outermost energy level. That's just energy speaking, not very stable. So like anything else, you start with the lowest level. So we start building and putting electrons in the first energy level, which is depicted here. And then you go into the next energy level, okay? And then so on and so forth. It's like layers of an onion, okay? Now, each box here represents 2 electrons. I can put 2 electrons in each box, right? So the very first, and I'm going to denote those electrons as arrows. It's an electron. So the very first element is element hydrogen. Hydrogen is number 1 proton, 1 electron, okay? And so its electron occupies the 1s1 orbit, and I denote that by an arrow, okay? Then I go across the periodic table, and if you look at the periodic table, it goes from hydrogen all the way across to helium. Helium is element number 2. 2 protons, 2 electrons. So I can depict that by putting an arrow, but I got to do it properly, because there's another principle that we don't talk about in this class in Chem 130. But when you get 2 electrons in one orbit, what's happening is one orbits in one direction, and then the other electron orbits in opposite direction, okay? So I depict that by putting a down arrow, just showing that there are 2 electrons in the 1s, and guess what? In the letters S, P, D, and F, I do a superscript. That superscript denotes the number of electrons for that orbit. Since we got 2 electrons in the S, I do superscript S. So for helium, the electron, what we call the electron configuration for helium, is 1s superscript 2, okay? Now, at this point, we're in element number 2. And if I go to the next element, which is lithium, it has 3 electrons, right? And 3 protons. So now I'm in the second energy level. Note where lithium is. It's in the second energy level. And it's in the first group, 1A. So that 1A tells me that there's only 1 electron in their outermost shell, okay? Outermost shell, which is in the second energy level, in the first column, which is 1 electron, there's 3 total electrons for lithium. 2 of those total electrons are in the first energy level, the 1s2. And the last one, the outermost one, is in the second energy level in the s orbit. We fill them up in the order of S, P, D, and F. Right now we fill up the S first, okay, and then we move across. So that shows the number of electrons for lithium. Now go one more to beryllium. Beryllium has 4 protons, 4 electrons. It's also in the second energy level. And so I need to add 1 more electron, okay? And I fill up my box of S before I go on to the P, okay? And so now beryllium is in the Roman numeral 2A column, right next to lithium. And so that means on the second energy level, there are 2 valence electrons depicted here by my arrows, 2 arrows. And then the other 2 are in the next energy level inside. Okay, you see that? All right, which brings me to go across the periodic table. I'm going to bring the periodic table here in a second. To boron. Boron is number 5. 5 protons, 5 electrons. All right. Now, as I go here, I start now to fill up the P because I can't put that 5th electron in the S. Why? Because the S is full. I can only put 2 in there. So the only place that extra electron that boron has, because it has 5, has to go into the P orbit and the first box. Okay. And so now check this out. Go to where boron is, number 5. Go to that full column and look on top. It'll say Roman numeral 3A. What that tells you is boron has 3 electrons in the outermost shell, which is energy level 2. And there's 3 of them. 2 of them are in the S orbit, and 1 of them, guess what? Is in the P orbit. Okay? All right. So right now, that's boron. Now go over 1 more from boron and look, and it's carbon. Well, I cannot fill the boxes like in the S. I need to fill the S first before I move on. Well, here I cannot put that extra electron of carbon in the same one that already has 1. So I just fill up another box. I fill up another P orbit. Okay. And so carbon is number what? 6. 6 protons, 6 electrons. Look at the group it's in. Go all the way up to the top. You see group number, Roman numeral 4A. That Roman numeral 4A tells you now that it has 4 electrons in the outermost shell, which is, again, also the second energy level. Okay? And of those 4 in the outermost shell, 2 of them are in the S and 2 of them are in the P orbit. And then the other 2, okay, are in the next shell in. And so continue again. I'm going to go across the periodic table. Next one is nitrogen. Nitrogen is number 7. 7 protons, 7 electrons. So here I just continue to fill up the box with my arrow to represent all the electrons. Now, look at the group that nitrogen's in. Nitrogen is in Roman numeral 5A, right in that whole column, okay? That tells you there are 5 electrons in the outermost shell, which, like carbon, happens to be energy level number 2. And those 5 electrons, 2 of them are in the S, 3 of them are in the P, and then the other 2 obviously are in the inside orbit. So you see how we start building them up, okay? And if we continue with oxygen, guess what? All the P's are full now. So now we can go and start filling up the ones that are any of these boxes. I'm just going to pick the first one and stick 1 in there, okay? 1 arrow. So oxygen is number 8. Look at the group number it's in, the very first, the Roman numeral. It's in group 6A. what that tells you is this: 6 valence electrons in the outermost shell. Sounds repetitive, okay, but I'm gonna keep emphasizing the point. Are there not 6 on the outermost shell? Yes, there are, okay? And 2 in the innermost shell. And also, keep this in mind. That magical 8, the goal here is for the atoms to want to gain electrons or lose electrons to obtain that magical 8. And if we, as we're moving across the periodic table, we are filling up the columns, the suborbitals, right? Because 6 and 8, as we fill them up, we're getting close to that magical 8, okay? If we go all the way across to neon, now neon has 10, oh, that's the wrong way, I wrote the arrow wrong way, okay? Neon has 10 electrons. Does it not? It's in group, it is element number 10. 10 protons, 10 electrons. Of those 10, okay, what group is that in? What group is neon in? Is in group 8. Of those 10 electrons, 8 of them are in the outermost shell. And you can, and they're depicted. Of those 8, 2 of them are in the s orbit, and 6 of them are in the p orbit, for a total of 8 electrons in the outermost shell. And guess what? It has achieved that magical 8. And that is why neon, this is a noble gas, is very, very stable, because all of the orbits, all the electrons have filled up the orbits for neon, okay? It's happy now, it's trying to maintain that 8. If we go back one and just had fluorine will have one of these electrons I put will be gone. It has room for 1. It's driving, it wants to gain 1 electron to give you that 8. And that's why fluorine has a tendency to gain electrons, but because by doing that, it has filled the outermost shell for itself and created a more stable material, which in this case is the fluoride ion, okay? On the other end of the spectrum, when we first started, we had the lithium. Remember, we have 1 arrow? Well, ask yourself, Mother Nature, would it be easier to gain 7 electrons to fill up that 2 orbit, or is it easier to get rid of 1? Well, definitely easier to get rid of 1. And that's why lithium, who has a tendency to want to get rid of that 1 electron, because it takes energy to maintain that outermost electron out there all by itself, and would even take more energy to bring in 7. It just wouldn't be very stable to make that happy 8. There's not enough protons to help stabilize, not enough neutrons to help stabilize that whole thing. And so lithium, being a metal, has a tendency to lose electrons. And when in doing so, now the next shell in is full and it's stable, okay? So the driving force is to help me get that magical 8 or that magical 2 for only a select, because some elements can't get, there's no room to get 8 electrons in the outermost shell. And like hydrogen, its drive is to get a happy 8, a happy 2. It has a duet rule compared to octet. But the rest of all the elements, its driving force is the octet. All right, so this continues, and you're at neon now. And guess what? If I go around the horn and I go to sodium, it is in the 3rd energy level. Look at the periodic table, okay? It has 11 protons, 11 electrons, and it's 1 electron now. The only place it can go is the next energy level. And that's why sodium is in the 3rd energy level, because it's going to maintain that 1 SO electron in the 1s orbit, okay? Which was similar to lithium when we got to lithium. Remember the first one we put in here? Okay, 1 electron, guess it looks, and everybody in that group, 1A, share the same property, and that is they have one valence electron. If we did potassium, guess what? Potassium would have one electron right there. Everything else would be full, and the potassium being in the 4 energy level, that one electron would be in the 1s orbit. Okay? All right, and being a metal, everybody in that group would want to lose that electron because there's too much energy to maintain more electrons in there. And hence, by losing an electron, they end up with a positive charge, okay? And that's also a metal. So now I hope you can pick up a trend here. I'm referring to periodic table.
I'm sorry, I have a quick question.
Sure.
So I think you were just about to answer it though. So basically, as you go across or down the periodic table, each element is just building on from the previous.
You got it. Exactly. You are building. That's why I started with hydrogen here and showed the electrons. So I went from hydrogen and then just building up. Okay. Some additional information that you put on your product table, let me bring that up, is as follows. Okay. Notice on the far left, I put the energy level to tell me 1. Now, how do I know S and P, D, and F? Well, I got it marked here to help you out. The first 2 elements in group 1A and group 2, think of those as the S elements, okay? S elements. Notice as I was going across and I went to 2s for lithium, that's where the first electron went, right? And then when I went to beryllium, the second electron, I filled up that box again to fill up the 2s electron. So I build up on it. And notice how many columns the S elements have, 2. And how many electrons can I put in the, let me demonstrate that here. How many columns in the S? There's 2. And how many electrons can I put in for the S elements? 2. The first one is S superscript 1. And once I fill up another one, the ones next to it become S superscript 2. Okay. Now over here, guess what? We call it the starting over here. And this is only true. Well, I won't go that far yet. Starting over here, notice how many, count the number of columns starting with number 3A. We got, starting with boron. Let me get my arrow here. Don't we have 1, 2, 3, 4, 5, and 6. 6 columns. Remember the P, think of these as the P elements, and the P can only handle 6 electrons total, right? And so I saw for boron, I got P1, go across to carbon, P2, P3, P4, P5, P6. Down here was S1, 2 columns, and then when I'm talking about, say, the next group, we're talking about S2. I'm not including the energy level because that depends on which element you're talking about. If I was talking about lithium, it would be 2S1. If I was talking about potassium, we're talking about 4S1 because everybody's in that same column. And 4 is because I identify where lithium is, and I know there's 7 energy levels. All right. Now, let's make it more interesting. If we go on the inner side, these guys have their own. I meant to put this one down. They all have their own name, but these are called inner transition metals. We're going to learn more about that, but I've highlighted them. I guess it's a purple color. Okay. Know how many columns you have here, starting from right here. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Call these the D elements, okay? That's where the D electrons orbitals come into play. And I start with SC first, its d orbit will be D1, and then across the table, across the periodic table, all the way to zinc, that becomes D10. Okay, and then let me choose a different color here. Going down here at the bottom, these guys have their own little name. We'll talk about that, but you will see here that there should be 14 columns here. I think I got the whole thing. 14 columns. Those are called the F. Think of those as the F elements. Okay, and there are 14 columns. So we got F1, F2, F3, F4, all the way to F14. Okay, so here I'm using the periodic table to help me write the electron configuration that we're going to write for each element, for whatever element's given. And we don't have to memorize anything. All we need to know is where they're at in the periodic table, what energy they have, and we can start writing the electron configuration. Okay. All right, so let's go back to this one here. And like you said earlier, you are building up. You start off with hydrogen, and then, as you move up the periodic table all the way to 118, you start building up on it. Now, the one confusing thing that I need to introduce here is, let me go back to the periodic table and zoom up a little bit. Okay. Now, I mentioned earlier that starting in here, we start with the D's, right? These should be D. We call these the D elements. Okay. Now, also notice that if we start with number 21, you don't have to worry about the D's until you hit number 21. Okay. If they ask you about number 20, well, that's great. Just do up to 20, and the D's don't come into play until you're asked, if you are asked, element 21. All right. The only thing to remember is this. The D elements, their energy level that you would think being in period 4, like the S and the P, you would think, oh, okay, so that would be 4D if I was talking about number 21. It would be 4D1. And that's a good conclusion you can make. However, unfortunately, that's not the correct. Because from the mathematics and so forth, the D energy level of that element is 1 less from the period that it's in. Okay? All right. Let me do an example here. We're talking about number 21. We look and say, okay, it's in the 4th energy level. So we would think, and it's in the first column, okay? So you go D1 and go across to D10. So we would think 4D1. That's a good conclusion that you can extrapolate from what you're learning, but unfortunately it's incorrect. You look at, when you get into these D elements, you look at the energy level it's in and just subtract 1, that's it. So it is, SC is in the 4th energy level. Its electron, yes, is in D1, but that energy level is 3D1 and not the 4D1, okay? If I were to do Y, okay, we can see that it's number 39, and we can see that it's in the first column of the D elements. It's also in the 5th energy level. We would think 5D1, but remember, for the D elements, subtract 1 from the energy level it's in, so it'll actually be 4D1. Okay, so on and so forth. Now, with respect to the F, it's analogous with what we just did, except instead of subtracting 1, subtract 2. Because the D sub energy levels, the orbits, are one less, are actually occupy the one energy level in from where they are, energy level in they are on the periodic table. So SC, for example, number 21 is in the fourth energy level. However, the D start off at 3D, okay? For the S, they come in 2. So let's say if, for example, you were doing this, but the likelihood not so high that if you were doing electron configuration for these elements, but if you did, okay, if you're doing P4, this would be F2, okay? We would think it's 6F2, but it's not. You got to subtract 2. So in reality, it is 4F2 to describe that. The next one over, 21, would be 4F3, and so on down the road, okay? And that's the only difference. The S and the P's, whatever element, whatever energy level you are in, that is the energy level. That is the energy level of that orbit for the S and the P. The D, subtract 1. The F, subtract 2. Okay. And that is why you think about it, okay, you see the D's here come in play in the third energy level, because originally the D's are, for these, they are really in the fourth energy level for these elements starting with 21. But that orbit is really 1 in. You understand? And the same is true for these S, that you would think that they're in the fourth period, but they're not. These are actually in the sixth period when those come into play. Okay, and over here they would be in the 5D originally. That's where that element exists in that energy level. But it's that orbit energy level. Okay, there's a difference. That is the element's energy level compared to the orbit's energy level for that element. Okay, it's either going to be 1 in for a D or 2 in for the S. Okay, so as I stated earlier, these orbitals, sublevels, S, P, D, and F, are nothing more than mathematical equations that you can take and plot. And what you get is a plot that looks as so. And what that does is that depicts a probability of an electron being someplace in that area, okay? Now, with respect to the metal, this particular area and this happening, you know, there are some scientists that don't really care for this theory, and there's some are all gung-ho about it. The difference is this, is in one moment, I just finished talking to you about how these electrons have to be at a very specific energy level, right? 7 energy level, 7, because they behave just like light. And then we talk about mathematical equations that talk about a probability of an electron being in a particular area in space. You know, 1 minute we're talking specific, next minute we're talking probability. And Einstein wasn't too crazy about this model. He just didn't feel that nature is very exact and very specific. And but nevertheless, like I stated, is the best model we have that supports the experimental data that we have, and it can change very quickly. All right, here's a picture of the p orbits. There's 3 of them, right? And they have this dumbbell shape, and there's 3 of them in the different axes: the X and the Y and the Z axis, right? And in there, you know, it's been kind of it doesn't look like this one here. This one we just treat it as a ball, the S orbits. And here we just, again, treat it as a ball, and we have 3 of them, okay, in the 3 axes. The D's and the F's, we don't have any pictures of those. These links don't work anymore. I've been trying to find some. There are some wild looking pictures. You know, they look like space stations, you know, from the future. Anyway, feel free to Google, you know, give me an image of an F orbital or D orbital so you can get some examples and you'll see how crazy looking they are. Okay, again, those are mathematical equations that depict an area in space of where there is probability in the electron being. Okay, which brings us to electron configuration. And I think I'm going to stop it here. I think I will. I will. Number 5 in slide 24. Okay, what this is, if you read ahead, is basically what I was doing with the boxes and showing the arrows. Okay, instead of doing it graphically that way, we're going to do it using the electron configuration, the 1s, 2s, 3s nomenclature, if you will, the way how to write it. And there is a diagram here that tells you that's the order of how you fill these electrons, and depicted by the green arrows there. It goes the 1s, the 2s, and then we jump over to the 2p, and so on and so forth. And here's the equation that I just talked about. And the one thing about that equation I want you to remember is,
here's the result from search.
So, as follows, is these d electrons, okay, or the s, and these d's, they don't come into play until you get those electrons. So if I stop at element number 20, only if I go into element number 21, which is the next one, do the D's come into play, and then 3D hops in there. Okay, so in the meantime, if you're not there, you don't need to write those letters. And you go all the way across to zinc, and that becomes 3D10, and you're done. And then at the end, you start back up with the P. Okay, does that make sense? Let me go through the periodic table here real quick to explain that. Okay, and so here, this is 3D10, okay, and this would be 3D1, okay. I know I'm in the fourth period. These are the D elements, so I go 3D1, and then I went across 3D2, so on and so forth. Once I get to number 31, I'm back to the P, and I'm back to the 4P1, okay? And then going forward, I go back all to the same energy level, because the S and the P, whatever energy level they're in, that's the energy level of the orbit. The D goes in 1, the F goes in 2, all right? And so be aware of that when you use that particular system. So, or you can use a periodic table, because I'll demonstrate that next time we meet. You can pick any element, and very quickly, based on the position it's in, based on how I describe the S, the P, the D, and the F orbits, based on the energy level it's in, based on telling you that the D's are 1 energy level in and the S are 2 energy levels in, you can get any element and very quickly write the electron configuration, okay? Or you can use that until, if you're more comfortable with this one, then that's fine too. Whichever works best for you is the ultimate goal. I'm just trying to simplify it and hopefully become more understandable. All right, so let's stop it here. We'll stop at slide 24. We'll continue on Thursday.